discuss sampling methods, but then we're going to take a little bit more time on the central limit theorem. Let's go ahead and review a little bit on population and sampling. In the population, we're talking about essentially every possible observation of a particular body or phenomenon of interest, and then the sample is a subset of that population. And why might we want to take a sample instead of the entire population? Well, here's some good examples right here, and we've talked about these briefly before. It would be very time consuming. Consider the census that we take every year, every 10 years in the United States, that how many people are involved in taking that census and how long that takes. The cost, don't know the cost of the census and probably wouldn't want to know, considering it's taxpayer money that's going toward that. Number 3 is the physical impossibility of checking all of the items. If we're talking about a healthcare study, for example, and we only have 2 or 3 researchers, and we want to get all of the United States population of men from age 35 to 65 their cholesterol level, it would be pretty impossible for us to get that data. And then the destructive nature of some tests we talked about is an example. A good example is the drugs testing. If we're testing a new cancer treatment drug, and all of the tests are destructive, if we need to test it to see if it's toxic before we give it to patients, if we use the entire population of pills, we won't have any pills to administer to our patients. And number 5, we haven't really discussed in too great a detail, but we did mention it briefly, that the sample results are adequate. It's been found statistically that over time, they've found statistically that the results that we get by a proper sampling methods are close enough to the actual population results of analysis that it's not worth it to go and do the population, even if you could afford to do it, and good appropriate sampling is sufficient. So how do we go about doing the sampling? Well, we're going to talk about a probability sample. For statistical validity, we're going to talk about the probability sampling, and that goes very back to when we were talking about evidence-based management. We talked a little bit about statistical validity. And a probability sample is a sample selected such that each item or person in the population being studied has a known likelihood of being included in the sample. So if we're going to make inferences on a population based on the sample, wouldn't it be good if that sample that we're selecting is representative of the population? Well, the answer to that is pretty clearly yes. And so the idea is we want to try to get a representative sample of our population in order to do our analysis. And sometimes there are cases where we would want to use a non-probability sample, where we use some sort of judgment based on the person selecting the sample. And the most commonly used probability sampling methods are the simple random sample, the systematic random sample, the stratified random sample, and cluster sample. And we're not going to go into great detail on these. I'm going to provide you some reference slides for these, but you can also find information in your textbook starting in page 267. If you want, you can pause the video on each of these slides. Okay, another attempt at humor. And since we're taking a portion of the population when we sample, it's unlikely that the sample mean will be exactly equal to the population mean. The same goes for standard deviation, variance, and any other of the calculations that we would calculate from the sample. And the difference between a population parameter in the corresponding sample statistic is called sampling error. And so what are these terms, population parameter and sample statistic? Well, if you just think PPSS, that will help you. But we're talking about if we have a population standard deviation, that is a population parameter, and the sample statistic would be the sample standard deviation. And the difference between a population parameter and the corresponding sample statistic is called a sampling error. Let's take a look at a slide that gives us a little bit more on that. So I used the example of the difference between a sample standard deviation and the population standard deviation. So we have the sample statistic of the standard deviation, the population parameter of the standard deviation. So an example might help here is, let's say we took the mean age of all of the students in the healthcare program and all of Trinity. Well, if we had the population and we had all of the students, then we could calculate out the population mean, or the mu. The other thing we could do is just take a sample of a representative sample of the population. So let's say that there are 100 students in the healthcare administration program, and we had a population mu of age 25, and we sampled 10 of those students, and we get an X bar, or our sample statistic of the mean, and we find that it's 23, and so the mu was 25 and the X bar is 23, so we have a -2 is our sampling error. So the sampling distribution of the sampling mean is a probability distribution consisting of all possible sample means of a given sample size selected from a population. So how can we make an accurate prediction about the possible success of, say, a newly developed pharmaceutical? If we sum the sampling errors over a large number of samples, the result would be close to 0. And that's true because the sample mean is an unbiased estimator of the population mean. And what that means is that if we took all possible sample means and averaged them together, the average would equal the population mean. So if we organize the means of all possible samples of our chosen sample size into a probability distribution, the result is called the sampling distribution of the sampling mean. Let's walk through how we can construct a sampling distribution of the sampling mean. So we have Private Healthcare Practices LLC has 7 employees, and that's the population. And we're only using this as an example so we can see how we construct this, but we would not need to do any sampling if we have only a population of 7. So the hourly earnings of each employee are given in the table below, and these are the questions we want to answer. And you can pause them if you want to read them. Let's start answering those questions. So we calculate the mean, which is $7.71. So how did we do that? We added up all of the values and we divided by the number of employees that we have, which is 7. So we get $7.71. We determined the possible number of combinations of samples that we could have, and we use this formula here, which is also in your book, and we're not going to go over that. Just realize that you can plug in the values, and this is n factorial divided by n factorial times n minus n factorial. So it comes out to 21 possible samples. So next we determine the 21 sample means from all possible samples of 2 that can be drawn from the population. This is why we only use 7 employees, because you can see how busy this gets. So here are the 21 sample means from all possible samples of 2 that can be drawn from the population. Now normally you're not going to capture every possible combination of samples that you're able to get when you're working on a project or a research or a study. The point here is to show how we can build the sampling distribution of the sample means. So then we use these 21 sample means, and we use those to construct a probability distribution. Here's our sampling distribution of the sample means and the probabilities associated with that. Next, we determine the mean of the sampling distribution, or the sample mean, by summing the sample means and dividing the number of samples. The mean of all the sample means is usually written by the mu sub x bar that we see over here. Notice it's the same as the population mean we found 3 slides earlier, $7.71. So we actually took here the mean of the entire population of 7 employees, the salaries. And then we went and built the sampling distribution of the sample means. And we took the mean of all of the sample means, and that's, again, the mu sub x bar. And we found that it comes out to $7.71 as well. So the mu indicates that it is a population value because we have considered all possible samples. And the sub x bar indicates that it is the sampling distribution of the sampling mean. So from these calculations, we can make some observation. So we can make these observations. The mean of the distribution of the sample mean, $7.71, is equal to the mean of the population. The spread in the distribution of the sample mean is less than the spread in the population mean. So as the size of the sample is increased, the spread of the distribution of the sample mean becomes smaller as well. So here's our population distribution that we had, and you can see the spread here, whereas the distribution of the sample mean is much tighter. Well, maybe not much, but a little tighter. And the shape of the sampling distribution of the sample mean and the shape of the frequency distribution of the population values are different. The distribution of the sample mean tends to be more bell-shaped and to approximate the normal probability distribution. So this gives us a good segue into our discussion on the central limit theorem. And the central limit theorem states that for large random samples, the shape of the sampling distribution of the sample mean is close to that of the normal probability distribution. The approximation is more accurate for large samples than for small samples. So knowing that we are creating a distribution, or the shape of the sampling distribution is close to that of the normal probability distribution, we can look at some of those characteristics of the normal probability distribution and factor those in when working with our sample distribution. So the central limits theorem states that if all samples of a particular size are selected from any population, the sampling distribution of the sample mean approximates a normal distribution. And this approximation improves with larger samples. So if the population follows a normal probability distribution, then for any sample size, the sampling distribution of the sample mean will also be normal. If the population distribution is symmetrical but not normal, the normal shape of the distribution of the sample mean emerge with samples as small as 10 observations. If a population distribution that is skewed or has thick tails, it may require samples of 30 or more to observe that normality feature. The mean of the sampling distribution is equal to mu, and this variance is equal to the sigma squared divided by n. Let's take a look at some figures that might help our understanding a little bit. So if we have a population that's distributed like this, our sampling distribution, when we have an n of 2, in other words, we have taken 2 observations, is going to look something like this, possibly. And if we capture 6 observations, we're going to see it start looking a little more bell-shaped, and then the n of 30 gets even more so. And this is a little bit distorted because it's squished onto the page a little bit, onto the slide, but this would be spread out just a little bit more on the normal distribution. Now, if our population was shaped like this, and we take two sampling distributions, it might look something like this. And then at 6 it might look something closer bell-shaped, and so on like this. Same for this distribution of the population and this distribution of the population. We see as we get more and more observations, it becomes more and more normally distributed. So notice that regardless of the shape of the population distribution, the sample distributions all start to converge on a normal distribution shape. And most statisticians consider a sample of 30 or more to be sufficiently large for the central limit theorem to be used. And I'll share with you a couple more reference pages. We'll only briefly stop on these. But I do encourage you to take a look at this simulation here. If you go to the Khan Academy link that I have here, he actually refers to the Rice Lab statistics example, and you can kind of play with this to see how the sampling distribution of the sample mean and the central limit theorem work. This is what you'll see on the Rice Labs page. And you might want to pause on this and look at this. Now I'm going to quote from page 285. And this is to just talk about the standard error of the mean. It can be demonstrated that the mean of the sampling distribution is the population mean. That is, the mu sub x bar equals mu. And if the standard deviation in the population is sigma, the standard deviation of the sample means is sigma divided by the square root of n, where n is the number of observations in each sample. So let's look at the standard error of the mean. And the standard error of the mean is using the sigma to indicate that it's referencing the population, and then the sub x bar to indicate that it's the sample means distribution. And the mean of the distribution of sample means will be exactly equal to the population mean if we are able to select all possible samples of the sample size from a given population. In other words, mu is equal to mu sub x bar, which is pretty much what we showed in the example of the 7 employees. We also saw that there will be less dispersion in the sampling distribution of the sample mean than in the population. And as the sample size increases, the standard error of the mean decreases. And all of this discussion about the sampling distributions, the standard error of the mean, and etc. are important because many business decisions are made on the basis of sampling results. In business, we take a sample and we gather our sample statistic. We compare the statistic to the parameter, and is the difference due to random sampling error, or is a statistically significant difference going on? Is there a statistically significant difference between the two? And using some of the ideas we discussed previously, we can compute the probability that a sample mean will fall within a certain range. We know the sampling distribution of the sample mean will follow a normal distribution under the two conditions listed on the screen, which is number 1, if a population follows the normal distribution, the sampling distribution of the sample mean will also follow the normal distribution. And number 2, if the shape of the population distribution is known to be non-normal, but the sample contains at least 30 observations, the central limit theorem guarantees that sampling distribution of the mean follows a normal distribution. The z-score looks similar up here to what we've seen before, but there's a slight difference in here in that we now have an x bar minus mu divided by sigma instead of the x minus mu divided by sigma. So we are interested in the distribution of x bar, the sample mean, instead of x, the value of one observation. And in the denominator, we use the standard error of the mean of n observations. So we have the standard deviation divided by the square root of n instead of the population standard deviation. So this is how we get our z-score when we are trying to determine the distribution of x bar, the sample mean, instead of x, the value of one observation. Let's put this into an example. Here we have our scenario, and you can pause it to read this if you'd like. So on the point is we're trying to fill soda bottles, cola bottles. The actual amount is critical, but it varies a small amount from one bottle to the next. They don't want to underfill their bottles because that'd be bad publicity and bad for the customers. And on the other hand, it can't overfill each bottle because it would overflow. Records indicate that the amount of cola follows the normal probability distribution. The mean amount per bottle is 31.2 ounces, and the population standard deviation is 0.4 ounces. At 8 a.m. today, the quality technician randomly selected 16 bottles from the filling line. The mean amount of cola contained in the bottles is 31.38 ounces. Is this an unlikely result? Is it likely the process is putting too much soda in the bottles? To put it another way, is the sampling error of 0.18 ounces unusual? And the too much gives us an indication that we might need to look at the positive extreme values. So here are the values that we need pulled out of the equation, or the scenario that is, to put into the equation. And here's the equation. Oops. Here are our values. We plug in those values into the formula. So our x bar is 31.38 minus our mu of 31.20 divided by our sigma, which is our standard deviation, population standard deviation, divided by the square root of n. We calculate all of that out, and we find out that our z value, this is just part of the equation, step 1, is 1.80. So the numerator is our sampling error. The denominator is the standard error of the sampling distribution of the sample mean. So the z-value expresses the sampling error in standard units. In other words, the standard error. So now that we have our z-score, what do we do with it? Well, we look up the probability in Appendix B1, page 764 of our textbook, and we find that our probability is 0.4641. The probability is 0.4641, but what is that really the probability value for? Well, remember, in our textbook, it goes from the mean out. So that's the probability is 0.4641 from the mean to this point here, up to the 31.38. which is what we got as our x bar. So if you remember back, we're looking at seeing, is this likely that the process is putting too much soda in the bottles? Is that, oops, where did we go now? Is the sampling error of 0.18 ounces unusual? So what we're looking at now is that this 0.4641 value is to get us to the 31.38 mean value. In other words, a z of 1.8, a z-score of 1.8. But we want the probability of z value greater than 1.8. And how do we determine that? Well, if you remember our normal distribution, it's symmetrical, meaning each half is the same, and the total value of all of the distribution is 1.0. So that means 0.5 is on this side, 0.5 is on this side. And if we have 0.4641, we can subtract that from 0.5, and we determine that the remainder is 0.0359. So what do we conclude from that? Is this sampling error of 0.18 ounces unusual? Well, it's unlikely, less than a 4% chance, that we could select a sample of 16 observations from a normal population with a mean of 31.2 ounces and a population standard deviation of 0.4 ounces and find the sample mean equal to or greater than 31.38 ounces. And if you want to review this in your textbook, you can read that in page 288 of your textbook. And to read what I just said, you can find it on your next slide. So we've concluded that the process is putting too much cola in the bottles. And we'll go into this in greater detail later on, but this concludes our video for this episode or this chapter.